So let's go this time this way. The truth table and the minimization process. Let's obtain the sum of products or the product of sums, because this is going to be an option of the program. And then let's draw the circuit 3 or instead the circuit 4. And finally, let's go and test those circuits, for example, using Proteus or, writing the equation in Wolfram Alpha. It doesn't matter. One method or the other is going to be all right. So before, developing the circuits, let's have a plan. Let's see what we can do, or what we have to do one step to the next to get the circuits, even for these that looks that simple. Take it easy, okay? Here you are, the truth table as usual, the circuit C. That's the table. And this time we will design architectures based on sum of products or product of sums. And this means using the Minilog application. Okay, so those are the symbols for the same circuit C, the same set of inputs and the same output. So this time the purpose is to minimize the structure, not have the big structure, which is the one that you have if you follow the canonical equations. But let's see if Minilog can give us an idea of an equation that is simpler but is still, complying with the truth table. That's the purpose. So the plan is going to be like that. You have the truth table, okay? We will try to write the table instead of like this in paper. Let's write it in a text file, for example, and let's locate the text file into the project. For example, LCSD P1 section B, because this is all about section B, designing circuits, circuit C, and this time circuit C.tbl. That is the file extension to make it easy to remember for Minilog input tables. So once you have the file like that in this format, you will simply run Minilog, but here you will choose one thing or the other. You will choose sum of products, or you will choose to minimize in an equation in form of product of sums. And then we will have here another application, another hex file to convert the equation that Minilog has developed into an equation where the inputs and outputs are the ones that we like to have. So in the end, we will get a sum of products schematic or a product sum schematic, so that we'll be able to test them. So basically, what this software is going to do? Well, the software is going to automate by means of a computer calculator, is going to automate, and using espresso algorithms, the idea of getting rid of variables when you can, using Boole's algebra, eliminate them. For example, take this situation. For example, let's take two minterms here. For example, the minter 11 and the minter 15, both. You can imagine that the C is the sum of two minterms. And this means that you've got this term, D1, D0 naught, A and B, or D1, D0, A, B. So if you have this or, you know that you can extract here a common factor, D1, A, B, and then you can, place in brackets D0 naught or D0, and you know that this is simply a 1. So instead of a sum of two minterms, you have a final product, which is simpler because the DO has disappeared. Alright, so that is what the system is going to do by means of a computer program. Try to do it best to get the simplest expression possible, and that is going to be for sure easier if you do that using a computer or a calculator. So let's go and do it. So again, if you have in mind generating a file, this time in Minilog, go to the place from digsys, and the place is in P1, And here in Pig 1 Learning Materials you have a tutorial to talk about this software, Minilog. So run the tutorial or browse the tutorial to see what is going on here. And here you are instructions to go from one step to the next. Okay, so let's do that for the Scikit C. Here you are another one, which is the G out. So let's do it for the Scikit C. And the advantage, as usual, is that you can use this Scikit as an example table to copy and adapt. So this is what is recommended all the time. So go and save the file, the link as, and place it in the right location as we have established in the plan. So take it easy and organize that correctly. P1, section B, Scikit C, and here is when you can change the name of the Scikit P that you have found in the web into Scikit CTBL. And now you can forget the web and you can go back to the folder, and now is your turn to study the file, and here you can do it very well using the notepad or whatever else. Okay, this is a file, so you can use the WordPad or you can use the Notepad++ as you rather prefer, because it is a text file, so there is not a problem to edit it in one way or another. Okay, so you can change the Scikit P by the Scikit C. The inputs are not those ones here, but D1, D0, A, B. Use all the time the names that you have in your symbol. Never ever try to change the inputs and outputs, because that is going to be a complication. So you see, this comma means, or this apostrophe, this sign means that this line here is a comment. So W is a function of D1, D0, A and B, as usual. And then the output is W. And now you see, apart from these keywords, inputs and outputs and table, the three reserved words, the others are variables that you are inputting here. So now it's the same. You have to write simply D1, D0, A and B to every column and just write the output. And that now it is very simple. You can use columns or you can use white spaces or tabs. Doesn't matter very much. The point now is to copy the table that you know, which is 1, 0, 0, 0, I guess. And then here another 0, and here you have a 1 and a 1 and a 0. This is the 7. And the number 6 is a 1. And the number 7 is a 0. And then the 8 is a 0. And the 9 is a 1. No, it's a 0. And then the 10 is a 0 as well. Then the 11 is a 1. And then the 12, something like this. That is the same. You see? So that is the table format that we are talking here. Just the truth table that was in paper, now it is in this file. So now you can switch this, you can save that. Okay. And because this is a very simple application, you can install it directly in the folder of interest, for example. In the virtual desktop, it is already installed. You can call it because it's an icon in the desktop. But if you are in your local computer, you can very well install this device, this tip, into the right place. Scikit C, okay? So now you can go to you can switch off your text file, and now if you like, you can unzip this. Okay, that's the way to do it. You can extract all in this same place. And now you have this minilog folder, and that is all you need. What you need. It is a lot of folders here. There is too much folders. Okay, doesn't matter. Okay, basically you have two hexes here, the equation converter and the minilog. Those are the ones that you need to use. Okay, so now it's time for simplifying, because you have the secret table just edited now. So let's run the minilog and let's see what happens. We are going to find a solution from minilog, which is going to be I don't know why the machines say so. Run anyway, because it's a very simple, very well-known application. Just a small window to input the data. Takes time. I don't know why it is running that slowly, but you know, in the end you have to have your window. That's the window, okay? So now it's time to open the file that you are interested in, which is, you see, TBL, the one that you've been editing. And now the output format of this minimization is going to be logic equation. Okay, you can choose table, but since now we've been using table, but now because we have this equation converter, we can use logic equation. So logic equation, you know, single output mode instead of multiple output mode, because it doesn't matter now because you have a single output W, so single output mode is okay all the time, even if you have multiple outputs. And then you see here minimization result, sum of product or product of sums. Each one of them is going to generate a different equation, so a different second. Let's start with the sum of products, which is going to give you the Scikit-3 architecture. So that said, you can go run and you can check that the file is the right one, edit it, you see, the file is the one that we've been editing, a 1 in the 0, a 1 in the 5 and the 6 combinations, another one at the 11, and then the 13, 14, and 15 combinations, and a final end. So everything is right, okay? So you switch off the file, and now instead of editing, you can minimize, and now the machine works that way. Very easy. You have the final equation that we are talking here, but you see the machine has changed the variable names, and that makes this output very impractical. You can just change then every variable according to this table one by one, but let's do it automatically, okay? This is what did one of your colleagues the last semester, Gerard Nadal. So this is what he did, you know, this equation converter. So we can now stop running minilog, or you can leave it here aside. Now the machine has generated your EQ output. So now is your turn to run the equation converter like this. You run anyway the software, and now the machine is going to ask for the file of interest, which is that one here, Scikit-3 EQ. You say open, and now you have the Scikit-3 corrected txt, which is the expected solution. So now you can click it, and that's the right answer, okay? This is the equation that we are looking for here, right? So this guy, Gerard Nadal, did us a great favor using this simple filter. He did that using Python. So very fast. We have this naming translation. So it is great because here you are now a product, which happens to be just like that, just a minter. And then you have 3 more products. So this is the final product of sums. So very well, we will run now the same stuff for getting the other circuit, you see? So this is a project because you have a circuit. You can go now and check it and finish with this project, but because we are here at this point, we can just get that name changed, you see, corrected, and this is SoP output, that's okay. And now we can run Minilock again. We can go back to Minilock, and here in Minilock we can start with the logic equation. You see, you have still the same input, so now you can run logic equation again, but single output mode, but now product of sums. So you can run the minimization. So very well, now you have another kind of equation. You see, Z equal A or B or C naught, you see, with the names changed. So let's run again from this output. Now you can get rid of Minilock as well. So now you see what is the output from Minilock is this circuit C equation that has been rewritten, you see, it's like this, a product of sums. So let's go and translate the namings. So running again the equation converter, like this, and now let's use the same file because it has been renewed, so that's the one that we have here as a product of sums. So you see immediately you have the new solution that you can rename now product sum of products, like that, underscore sum of products. So that's yes. So I did it product of sums. That is what I want to do here. Okay, so let's check it now. Click, and exactly this is a similar equation from the minimization of this truth table, but you see now that you've got here 1, 2, 3, 4, and 5 products, all of them of 3 variables. So very good. This is the output result, and this circuit is simpler than having the long list of 9 max terms. It has been in some way simplified. Okay. So now let's draw the circuits and let's test. So very good. We have developed the circuit now. We have from Minilock solution, we have C, which is OR of 4 products, and you know we have as well the C, which is another solution that consists of a product of 5 terms which are sums. So those are the 2 solutions that we have obtained from Minilock. And now what goes next is simply draw the circuit. For example, if this is the C, you can generate the literals. I did that now, you see, the columns that are all the literals as usual. If possible, never change to do the things in this way. Do it once and again in the same way. This is going to give you comfortability, and it's going to be easy for you to think that the circuit to draw is as usual. So once again, write or draw the columns that belongs to all the literals, and then you can use here the same columns, the same literals for drawing both. In one hand you have the circuitry, which is this equation, you see, this simplified representation, which is a single line and some crosses, taking the 4 products in this second level of gates. You see, those circuits are quite regular with respect the others that you can get using any kind of equation. Those ones, the canonical ones, and those ones also, the product of sums and sum of products, are very regular. They are that way, a column of literals. Then you have another level of gates, which is, for example, in this case, the products. Every one of the products that can be placed in this second line, this second level of gates. And the same happens here. If you have the sums, all the 5 sums can be placed in the second level of gates. And then there is the third level of gates, which is simply another gate. Here you have a final OR, which is ORing all the products, or instead, in this case, is a final AND of 5 outputs that is generating the product of all the sums. So both equations happens to be the secant C, and perhaps what is left here is the final connections of these sums. So you see, you draw the secant like this, and finally you annotate what is required. Here you have D0, D1, that way, this sum is D1, the other D0 or D0 and or A0, which is available simply here. This is A0. So this is your first sum. You see, this term happens to be D1 or D0 or A0. And the same way you can go through the second term, D0, that one, A, and now B0, that one, you see? And the third, D1 not, D0, and B, or B, that's the or B. And then the fourth term, which is D1, like that, A0, which is here, and B0, and finally the last term, which is this final sum, D0 not, which appears to be here, and then A and or B. So that's the final secant, okay? So what is left now that you know the development is finished, you've got the solution of the problem, secant 3, or but instead of one solution, 2 solutions for the same price. But now is your turn to test, because here you have an opportunity to try again using Proteus or using Wolfram Alpha or using the EDA, the electronic design automation tools for VHDL synthesis and simulation. So now perhaps is another opportunity, for example, for solving the secant 3 using Proteus. You can test this using the electrical simulation virtual laboratory Proteus, and you can go click in the 16 combinations to see if now the secant is the one that you have here is going to generate the same to table, and perhaps the secant 4 can be tested, well, in the same way, but perhaps you can using the VHDL, because that one is going to be the one that we will use from now on in chapter 2 and in project 2, project 3, and so on and on, right? So it's a good time to use it again, as we did the other day for the analysis. Now is going to be good for using the VHDL tools, this time for the designing process. You see, you have got a 2 table to design, and finally you have a secant structure. So you are following what is called here in this digsys, in this CSD course, the plan A, structural, and finally you have an equation. So it's time for translating this equation into VHDL, and so it's time for running the synthesis process. So you will see the RTL, which has to look like that, exactly or very similar to this, and then the final model sim project for generating a VHDL simulation, perhaps using even the same test bench that you have in mind from the previous method for example, because if the secant has the same picture, the same symbol, the same entity, you can reuse the same test bench that consisted of the 16 combinations. So this is yet another time for you for using or reusing this test bench, this time for trying to solve this architecture. You see, in the end, it happens that you have all the time the same entity. You see the way it is organized. It's quite systematic, right? That's a good thing for you. If you have to, think about the plans and everything, yes, all right, but keep in mind what is the same all the time, and keep in mind what every one of these plans, every one of these solutions is new. So this is where you have to put your attention. But as I say, let's go finishing this video. If it's time for checking the circuit that you have invented using the VHDL, just another opportunity for using the synthesis tool, the Quartus Prime synthesis tool, for example, and the Model Sim project to get a final timing diagram. And by means of the cursor in time, you can just annotate the full table and check if everything is all right. Testing the circuit, for example, the circuit 3 using Proteus is that simple. You have to just jump to P1, and down there you will find the tutorial with several example circuits that you can copy and adapt. Okay, so in learning materials you have this Proteus tutorial. You click here, and here you are examples. For example, the combinational circuit that you can adapt, and well, you have here as well the circuit W, which is pretty much the same as you need. So you save the file as circuit C and place it in the right folder. Okay, on the other hand, you need to complete the circuit using NANDs and ANDs and ORs. So perhaps it is good to see the full list of chips of this kind. So here in the learning materials, the same, you jump to electrical characteristics, and here you are, for example, a PDF with a complete list of chip references. So you click here, and so you can see, for example, if you are searching ORs, so you know that the 74LS32 is going to be the right one to take. The same as if you are liking to find some ANDs for the products. So you see the 08 and the 11 are going to be right for you if you keep using the 74LS family. You can do the circuit using CMOS families or other families, but if you keep using this all 74LS, that the advantages that you have here, all the models, so that is okay. So now you can go to your circuit C and change the name and click, it is circuit C. I already did that, so you only have to open the file and make the modifications. You see here you have W, so change it by C, the output C. You can go to the child sheet and now implement, you see, this product of 4 variables, which is indeed the min term 0. You see D1 not, D0 not, A not, and B not. This wire here can have a label which is the min term 0 if you like. You see, you can place a wire label, so this is the min term 0. And then the other products. So you have in this equation 4, and then the final OR. You see, even if you are organizing it using several chips of the same kind, 74LS32, and in the end, you see, the best way to do that in 10 minutes or something is to keep an eye on the table to pick up the right chips from picking components. Okay, 74 LS, and you see, for example, if your 08 is going to be an AND of 2 inputs. That way, you click that, and that is in your circuit. Okay, so in this way you can finish the circuit very well. It was already in paper, so now you can take a picture of this, and this is the capturing, the testing section, capturing the circuit, so that now you can go to the top and check if it's going to work or not. You start with 0, 0, 0, 0, 0, and you run the simulation like this, And now what you've got here is a 1, which is exactly what you need. A minterm, the minterm 0, and then you changes to the combination 0, 0, 0, 1, and you have a max term, and then the 1, 0, another max term, and the 1, 1, and the 4, and the like. So now you know that the 5 has to be a 1, and etc. You can go to the end. So that is a kind of a demonstration that the circuit that we have invented using Minilock, you know, the simpler, this circuit that is simpler is okay. So that's the final step. You simply now print the screen just a couple of times to demonstrate that, for example, this combination is the 11 and the 11 is exactly what you want, a minterm, and so on. So now let's go with the next one, you know. For example, you can add here text, very simple. You can say stop the simulation and attach the text. This is the circuit or 3 based on, well, you can do that, or it is a lot better if you do that kind of stuff using, you know what I mean, a pen and paper. So let's print the screen. If you have to go reporting this, it is better to print the screen with your chip of interest. And now it is the time for explaining that this is the circuit 3, you know, based on sum of products from Minilock. So in this way you finish the exercise very well, you know, customizing the pictures that you've got from computers, making them your own pictures. This is fundamental in a course like this, where you have to demonstrate all the time that you are working on it. Okay, so now let me continue to the end, solving the circuit 4, but using the other tools, the VHDL tools. So finally, the last step, the demonstration or the testing of the circuit 4 based on a product of sums using VHDL tool. So you know how to start. You have to go to P1 and try again with the learning materials. And this is something that you already did, analyzing the circuits. It is here, okay? So it is the VHDL tools that you have to pinpoint to find something similar to copy and adapt, because now you like to find a circuit based on equations, so you only have to change the equation accordingly to the new one that you've been finding. So you click here, and down there probably you will find a circuit based on equations. Okay, let's see. This is it, simple example to synthesize. So this is looks like a decoder, but doesn't matter. If you keep an eye on it, you see that the architecture is 6 or 7 equations or 8 equations. So very well, that's okay, because the only thing that you have to do is to change the equation. So let's go back and save this, save the link as, you know, it is going to be section B, circuit C, and now let's rename that. You better pay attention to these details because they are fundamental. This is yet again another time the circuit C, even if we are using the strategy or the architecture 4, doesn't matter. It is the table from the circuit C, so name it like that. And now you can go to the point, and this means editing this file conveniently with the Notepad++. So take your time, you know. For example, this is a test for the circuit for architecture. Take your time editing the text, because there is not a problem wasting, so it is not wasting the time, it is what you need to do. Test for the circuit for architecture in circuit C or something like this. Okay, doesn't matter very much, but so this is the project P1. This is design, and that's okay. So the library and use is all right. The entity now, you know, is not that one. It is going to be second C. Very well. And now let's copy this down there, paste, and the architecture of this is that. So now, you know, standard logic inputs, you know that you've got two of them, A and B. And then you have another input, which is D. Let's keep it as this way, a standard logic vector, 1 down to 0. So D1 and D0 is going to be as in the analysis vectors. That's okay. It's not a problem to do that in another way, but why not? So now you have the output C, which is a simple output. So you delete that section here, and that's the entity description. Now the architecture, it's going to be equations, but you know the circuit form, PoS, product of sums. So let's copy this name down there again. And now you see you have plenty of equations here, so let's keep a single one. And then what? Well, this is going to be the C, and now you see the style and everything. So how is going to be? Well, it's a good idea to place here, let's copy the equation to adapt, or to write, or to translate. This is the word I use all the time. We have an equation in Minilog as a text file. So let's copy the equation to translate to VHDL in this place. So this means going to the circuit, because it is circuit C corrected product of sums, like this. So you copy this equation of your interest in your file that you are editing as a comment, this way. So you see, you know now that you have 5 terms. So let's implement the first one. It's going to be D1, okay, or D parentheses 0, the index that way, or not A, like that. And now perhaps it is a good idea to place here a closing parenthesis and an and. And now you see that you've been the dynamics, you can get rid of these. And the comment is not necessary here. So that's all right. And let's open this parenthesis in this side, in the left. So this is the term, the first D1 or D0 or not A. And you see the other one. So now it's a good time to copy this again down there. The white spaces do not count. So this is okay. You see, let's keep it aligned correctly, and this way it works. So D0 this time, or A, and then or not B, I guess. This is the second term. And now if you like, you can copy it again down there. So this time is going to be not D1, you see, and another parenthesis, then or D0, so you copy that here, or B, that way. The next one happens to be that, which is another time something similar to this expression, you see? That is the translation I am referring to. D1 not A, or not A, and or not B, like that. And finally, it is a good idea to align this. I insist on this because in this way, if there is a mistake, it is 1,000 times better to find it. So that is going to be the last one. So here is where you can place, no, it's not, yeah, it's the last one, but it's D0 not D0 that way, or A, or B. Very good. So 5 terms, perfectly aligned, and this is the equation translated to this special format or syntax that is VHDL. Okay, if in the end it's not working, you only have to go and review again the terms, because it is easy to make a mistake here. But that's the final circuit. You see, that's the source file that you will introduce in Quartus Prime. Okay, so let's do it now. Let's just start a new project. Let's select the chip from the list. For example, there is no problem here to go to digital. Let's go back to electronic devices, and here you can click Intel, and now, for example, you may use the Max 10 or the Max 2 or even that one, the Cyclone 4. Okay, no problem for this, because it's that simple, the circuit, that any chip is okay. So we are in Quartus Prime, File, New Project Wizard, and that is because we are going to start a new project in this location, C, no, it's not the C, but the L, CSD, this course, P1, Section B, Circuit C, that's the location. So let me select it, and now the project is going to be Circuit C underscore PRJ, and now the top entity, you know, is the Circuit C. So you say next, empty project, and let's add what is here in this folder, and this is what we've been editing, the source file. You say next, and now let's pick up, well, doesn't matter, but if you like to get the Cyclone, it's not a problem, because it is just for this time getting the real thing. Okay, so copy the name of the chip and paste it that way. So now it is that one. You see, you say next. The simulation is Model Sim Altera, VHDL is the language, next, and finish. So now the project can be synthesized in order to see, when analyzing the circuit structure, if some mistakes are made or detected or whatever. So now everything is all right. So you can see the compilation, Circuit C. So now it's the Circuit C. So you say start compiling. So here you are, the final results, 0 errors. So now it's time to go to Tools and inspect the RTL, because the RTL has to look very similar to what you've been inputting as an equation. So exactly, you see, you have a schematic which is pretty much the same that you wrote in the architecture. Very good, you see, so this is a good sign. You have an AND of 5 products. So now you see what is left now is simply to go through the testing of this device by means of another project, this time using Model Sim. So let's tackle the next task. And if you have, from a previous example, the test bench is okay, you can use it the same. And if not, no problem, you can just do it again, because it's that idea now what you need. Perhaps go several times running the same kind of automatic task. So you have to go to processing, start, and start the test bench template writer. And now the machine is going to write this feature that we called test bench, that is a closed box where you are placing inside the component and the test, along with a process that has the stimulus of the signal. Basically, it's something like this. And you know that you can take this stimulus, which is what you have to write from the web. So let's see if we can copy something similar to adapt from any web page that we have available, right? And that is not going to be very difficult because we can go back to the home P1 again, and this is about the method 4, right? At this level is the method 4. So here you have this lab, and this lab was about running the synthesis process. This is what you've seen here, and now you have the scikit-w testbench and the min-pulse variable, and here you are an example. You see the idea. I insist on this. Take your time processing what you are doing, okay? So the idea is just like that. It is a picture is 1,000 times better than a complicated speech. You see, this is what we have in mind. A closed box with a unit under test. This time is going to be the scikit-c, and a single process to input the 4 variables, you know, the 4 signals, and then let's pay attention to the waveform viewer, the wave, so that we will go with the cursor to see if every input combination is right or not. That's the job, okay? So now we can go to the folder, and in simulation, model sim, to do it all the time the same way. Let's rename that testbench VHD as scikit-c testbench.vhd. That's my proposal all the time. So this is what, yes, let's change it and something else. Let's Control-C, let's copy it to the project file. So here you are now both the test bench and the component and the test. So now it's time for you to run a model sim project. So this has to be easy to find. So it's going to be model sim, the edition 10.5b, that one, okay? Quartus prime, so that's the one, the good one. So let's open now this new simulation environment to start from scratch a brand new project to simulate this structure. And meanwhile, we can go and fetch something similar from the web, and this has to be, for example, this circuit here. This is a good place to copy something, because, for example, here we have the constant, okay, the min pulse, the time in which every one of the combinations of the t-table is going to be stable and simulating. So now it's a good time to start the project in this new window, close this initial window, and now let's do that thing of close everything that was here before. Yes. So now file, new again, project. The project name, it's what you know very well. Let me place it in the P1 section B scikit-c. Okay, so this is going to be the name as well. But now the name of the project is scikit-c. Again, you know what I'm doing here is scikit-c functional simulation, and work functional is the library of components that are going to be generated here. Okay, and in this way it's going to be very easy identified in the long list of library components that you have here available. So you say so, and okay, and now what goes next is to add existing files, precisely the ones that you have here in the project folder. You see, if you are working like this, organizedly, and paying attention on where you are saving and you are taking the files, is the best way to go. So you open these 2 files and you add them to the project, and then there is enough. Okay, so now you can go to this window where the project files are located, and you can click the tab Compile All. So very well, no errors. So now you can open the test bench and edit it correctly. You can open the test bench and you see it's been automated, almost everything, but you know that after the component description before the begin, you can go to the web and copy the constant here, and you make it easy. For example, 10 microseconds, and let's do that way. So you can run the full truth table in, if one combination is going to be around 10-20 microseconds, you can run the full truth table multiplying this number by 16, okay? So let it be 300 microseconds or 400, doesn't matter. So now let's go to the section begin. This is automated, and now you have down there the init process and always process that you better delete, okay, and replace. But what you know is in the web page, in the example from the web. So you see, here is where the stimuli goes. So you better go to the web and take it. You see, for example, this way. Control C, the full process, that is going to be the stimulus process. Control C, and now you paste it here. And now you only have to pay attention to the truth table. So very well. Now this time we can do it that way, 0, 0, 0, 0. The second combination is going to be 0, 0, 0, 1. The third combination is going to be 0, 0, 1, 0. The third combination is going to be 0, 0, 1, 1. And, well, there is no, that's okay. It has to be, you know what it has to be. For example, in 0, 0, 0, you know that it has to be a 1. And in here, it has to be, the output must be a max term, and so on. So this is the 3, okay. And so you can finish the file to the end with the 16 combinations. So you can delete that once, now that you know how it works. And you can copy them all. Okay, the 0, the 1, the 2, and the 3. So you can copy the 4 of them. Control C and paste it here. So now you can have this second section of the table like that. This is the number 4. Okay. This is the number 5. This is the number 6. And finally, this is the number 7. And now yet again another time, you can copy the 8 of them. And you can separate that, but another line of comments. And finally, in this way, you know what you are doing here. It looks like that is here the point. So now it's going to be the 8, the 9, the 10, 11, 12. Well, this is not right. 12, let me finish. This is going to be 13, 14, and the last one, 15. You see, it's not that complicated. When you have a little practice with this, it is easy. So this is the stimulus process that is going to input, you see, the 16 combinations of the truth table. So now it's time for saving the file, closing the editor, and going back to the model sim. And now let's see if everything is all right. Compiling again, no errors. So good, because now it's time for simulating. You can start the simulation now of what exactly? A design. Which one? Well, it has to be on the list. Work functional. You see, the test bench that is going to contain the scikit-C as the unit and the test. You say OK. And now you have here the new window where you can select with the right click all the devices. You see the A, B, C, D. What is this exactly? A, B, C, D? Nope. Let's see what happens. Let's see, add to wave all the items in region. So this is the wave. So let's arrange the wave. Let's add a divider. This is going to be the output. So let's place the C down there as output, and let's place the D, the first. So you see you have D1, D0, A and B, the 4 inputs ordered as usual, and this is the C. The variables has to be ordered correctly, because remember that you like to extract from this simulation precisely the truth table in this order exactly. So take your time to do that job of organizing in the right way the variables. You see, D1, D0, A, B, and the output C. And now it's time for running. You know that how much time you've been assigning to the min pools. So now it's time for run, for example, 300 or microseconds. So let's see what happens with wave. The simulation has finished. You are in the end of this time. The values look stable, but now is for you to do that zoom full, and that's it. Okay, you can even change the color of this. So properties of this signal format, no, it's going to be view, wave color, let's just color it in red, that way. So to make it clear that this is the output, so look at this. Let's start 0, 0. This is the, the capturing of the truth table now, the last step of this testing. So you had the circuit, and now let's see if it's the circuit that you've been inventing, the circuit 4 that comes from Minilock, works or not. You are inputting now. You see the values here, 0, 0, 0, and the output is 1, which is okay. Then you are inputting 0, 0. It is better perhaps to get this way, 0, 0, 0, 1, 0, then 0, 0, 1, 0, 0, 0, 0, 1, 1, and then the number 4, 0, 1, 0, 0, another 0, perfect. Then the number 5 I see, 0, 1, 0, 1, and this is a min term, and the number 6 the same, 0, 1, 1, 0 is a 1. Then the 7 is a max term, the 8 the same, and the 9. And perhaps now the 10, you see 1, 0, 1, 0 is another 0, but the 11 is finally another min term. And then the 12. The 12 happens to be max term, very good, but you see you have not simulated simulated enough time to go to the end. So that's not a problem. 300 microseconds was not enough, so you can run again 300 more. So now you go back to your wave, and now you can zoom all if you like, and you can go zooming a little bit where you were, and this is where you were, 1100, 0, and then 1101 another. Now this time is the 13, which is 1, the 14, and finally the 15. So you see the circuit that you've been inventing, which looks like this in Quartus. Remember the circuit that you've been inventing, the RTL, that one is right, is okay. It is another realization using logic gates, given a structure, this time a product of some sums, that is generating the same table that you see here. So now finally it's time to print the important windows here. For example, that one is okay, and you know, it's time for annotating whatever you have to say here. The same with the circuit. That's another picture that you better take, print the screen, and you know, this is the circuit that you've been capturing. Okay. So that's all. That's, you know, perhaps is longer than expected, but this is because I pretty much like to focus your attention not in the tool Minilog, but in this idea of going through the 4 sections. This is a project-based course, and now even if you are at the very beginning of it, you know that's the way. 1, specify. 2, plan, take your time, sheets of paper, organize a flow chart of micro operations that you have to go through. First I have to do this, second I have to do that, and etc. Then take your time to develop, whatever the way, this case was, you know, running Minilog. And finally, once you've got a circuit, it is absolutely fundamental if you are designing projects, and that is perhaps different from an academic course when you simply hand in the development and perhaps the lecturer is going to correct what you are, you know, handing in. But this is not like that. Here in CSD, we are focusing absolutely everything in a project. So a project by definition must be tested. So you see, testing this circuit 3 and circuit 4 perhaps takes longer than inventing the circuit, but that is normal, you know, that is what happened. Testing something for real takes a lot of time, but this is the way it works CSD all the time. I will ask you, you will see that continuously, how has been your testing of the circuit that you've inventing, and that if the circuit works, that is perfect. Okay, because if it's not, no problem. You only have to go back and to find where the system fails. Perhaps some terms in the table are not as you've been expecting, because perhaps you have forgot some knots or some wiring here. But that is the normal situation. Go back and find the mistakes and redo the process to the end until something like this happens. Okay? The circuit that you've been inventing works in every single situation. So that's the perfect ending of this, you know, tutorial exercise. So thank you.